Alright, so welcome back. We're looking at this next example when we're solving simple trigonometric equations, and this is very similar to the last one. But what happens if I wanted to solve the equation for, say, sine x equals 0.6? And I don't know a ratio of 0.6 using my hand trick. Let's see, 0.6 would be 6/10 or 3/5. And although it does exist within the range of sine, right, the range of sine does occur, in fact, between -1 and +1, right? 3/5 does in fact occur up here somewhere. It doesn't land on one of my significant angles for sine. So let's see, let me once again just fill this out. Let's see, this would be 3 pi over 2, and here is my 2 pi. And sine, once again, starts at 0, goes up to 1 at pi over 2, back down to 0 at pi, down to -1 at 3 pi over 2, and back up to 0, and is a curve like so, something like that. Right, so if I want to figure out when is sine x equal to 0.6, alright, if here's my half mark, 0.6 would be somewhere like this, and I would be interested in when does that angle occur. Alright, now it incorrectly, according to my scale, appears to land at pi over 4, but it will in fact not be that value. So if I want to solve this for x, the only thing that can get x by itself here that would undo the sine, and I'll actually have to write some more room here for this, I would have to take the sine inverse of both sides. Alright, which is going to undo the sine function. Alright, recall that sine requires an input of an angle, and it gives us a ratio, whereas sine inverse requires the input of a ratio, and it will give us back an angle. So sine inverse of sine x actually would give us back just x, and I would get x equals the sine inverse of 0.6. And the way I could evaluate that, or at least get an approximation of it on a calculator, is using the second button, and above the sine button you'll see a sine to the -1, and that would end up giving us the value. We could then plug in 0.6 and hit equals. So we'd plug that in a calculator, and we would get x is about, and I've got 0.6435. Alright, and this is in radians, by the way, so actually I just want to indicate I'm in radian mode here. Alright, in order to get that. Alright, so that's 0.6435 radians. Alright, recognize that pi is 3.14 radians, so if you imagine me dividing pi into thirds, right, something like that, 0.6, this would be 1 radian, and 0.6 of that would be somewhere over there. So that appears to be a correct value for what we have based on our graph. So our reference angle is this 0.6435 value. So that represents this particular solution, but in order to find this solution over here, it's going to require a little bit more work. Now I can't just add like pi over 2 in order to get that. I have to actually consider reference angles again. Right? So once again, from 0 to pi over 2, this was the first quadrant. The second quadrant occurs between pi over 2 and pi. So if I want to find this angle, the reference angle would have been the difference between pi and that value, which happens to be the 0.6435. So I can actually calculate the other value by doing x would be approximately pi minus 0.6435. So let's see, this is one of our solutions, and I would get x is approximately 2.4981. as being the other angle where we have that 0.6 as a height occurring, or that 0.6 being the ratio of the opposite to the hypotenuse on our unit circle. Alright, but those are only these two particular values, the two significant, I guess, radian angles where sine happens to be that, where it occurs within one period of sine. But what about beyond a single period? We would also have it occurring in the future, right? And also in the past on the x-axis. So the way I could figure out that is, let's determine what the coterminal angles for those would be. So all solutions to this would be x is about 0.6435, and that once again is measured in radians, and I could find any other solution by adding 2 pi n that would represent the coterminal angles of this angle here, and the other solution, or solutions rather, would be the 2.4981 and add 2 pi n to find the coterminal angles there. And once again, n is any integer, right? So positive, negative, no fractions. And once again, I actually just want to point out 2.4981. If pi radians is 3.14, notice the 2.4981 does appear to be about where I'd expect that point to be, right? If this was 2 radians, 3 radians would have been around here, and that's about 2.5. So that did appear to land where I would have expected it to. Alright, so this is how we could, using inverses, we could find the reference angle and the other angle, which would occur within one period of our trig function, and then using both of those angles we can find all solutions to our problem, considering there would be the infinitely many along the sine wave. Alright, so I look forward to seeing you guys next example.